Hi everyone, this lesson is an introduction to the idea of using radians to measure angles. Now let's begin with this diagram. So I've got a circle here. It could be any circle. I happen to choose a circle with a radius of 5. And I've got a little point here on the edge of the circle, on the circumference, point B, that I can move. And I'm going to mark here in red the distance around this arc. So the arc length at the moment is 3.79. And at the moment, a radius of 5. The angle at the centre of the circle, alpha, is 0.76 radians. Now that's interesting. I wonder what radians are. Radians are a way of measuring angles. I'm just trying to stop there somewhere close to 4. Oh, I almost had it. That's close enough. So if my length around the arc is 4 and I have an angle of 0.8, it seems to me that the way we calculate the size of this angle is we take the length of the red curve, 4, and divide by the radius, 5. 4 divided by 5 is 0.8. Let's try if I can stop on 3. I might be able to stop on 3, or I'll get, oh, how lucky was that? So the length here is 3 divided by the radius 5. 3 divided by 5 is an angle of 0.6 radians. This is a length, perhaps in centimetres, and this is a length in centimetres. The unit of this doesn't really exist. The word radian literally means ratio of the radius. So divide by radius. It's the length divided by the length. It's a pure number. In mathematics and science, measuring angles in radians is much more convenient than measuring in degrees. In degrees, of course, you would know that to go from here to, say, this point would be a 90 degree or a right angle. And why was it 90? Well, it all has to do with the Babylonians. And the Babylonians, when they first thought about the Earth moving around the sun, they thought that it took exactly 360 days for the Earth to go once around the sun. Turns out they were a little bit off. We now know that it's 365 and a quarter days, but to their accuracy, they thought it was 360, and so they divided a full circle into 360 steps. Or degrees. Historically, that's where it came from. But this is a better system. Now, if I do go to a right angle, we can see it's a little right angle symbol, this number, 7.85, divided by 5, comes to 1.57. That may not mean anything to you at the moment. Let's keep going further. Let's go beyond. Now, if I get to the point where the red curve equals 10, almost there. It's very difficult to stop on the right exact spot, close enough. So approximately 10 divided by 5, we have an angle of 2 radians. Let's keep going to where it equals 15. Nearly there. Close enough for jazz. 15 divided by 5 is 3 radians. It's just a little bit less than a semicircle, isn't it? I wonder what the value will be when I hit the... there it is. 15.71 for the length of the curve divided by 5 equals... now that number looks a bit familiar. 3.14 is approximately equal to pi. If you think about it for a moment, that would be an angle of exactly pi radians. As I keep going around the circle, I'm coming closer and closer and closer. Well, there, we just went past 6. Right, so the red line is now almost a full circumference. We're up to about 30 units divided by 5 gives 6 radians. If I keep going closer and closer and closer, now I'm nearly up to 6.28. 6.28 would be 2 times pi. Unfortunately, if it jumps to the middle there, it goes back to nothing. It goes back to an angle of 0. So I can't show you the full rotation. Well, that's as close as I dare go. It's almost up to there, and trust me when I say it would be 6.28. Now let's take a little bit of a look at the reason why that would be the case. I've just got some diagrams there that I want to just, there we go. Here's some clear space to draw in. So if I did go all the way around the circle for that angle alpha, remember alpha in radians equals the arc length divided by the radius. And I'm just going to imagine here not that radius was 5, but that radius was r. What is the distance all the way around the curve? Well, that's the circumference, and the circumference is 2 multiplied by pi multiplied by radius divided by the radius. And so, yes, a full rotation is 2 pi radians. We just wrote rad for radians. And that's equal to, or the same as, 360 degrees. I'll say equivalent, not equal. Numerically, these are very different numbers. But 360 degrees is the same angle as 2 pi radians. Now, we could divide by 2 on both sides here. And this gives us our nice conversion factor that pi radians is equivalent to 180 degrees. We saw that on the little demo. When I was halfway around the circle, the angle at the middle was 3.14. What about 90 degrees? Well, if I divide by 2 again, 90 degrees would be divide by 2. Pi over 2 radians, wouldn't it? Perhaps if I went from, so that was divide by 2. Perhaps if I divide by 3, pi over 3, 180 divided by 3, that would be the same as 60 degrees. This is a good one to remember. Everybody remember this one. You can work out all the others you really want to from there. What if I divided by 6? 180 divided by 6 is 30 degrees. That's handy. What if I divided by, what if I went pi divided by 4? So 180 divided by 2 is 90. Divide that again by 2, that's 45 degrees. Now, all of those ones come from pi radians equal 180 degrees. And if I just put that back to, oh, oops, what happened? Try again. If I just lock that back onto there for a minute, yes, you can see that that's a 180 degree, and that's pi radians. Now, if you remember pi radians is 180, you won't go too far wrong, because you can quickly work out what 60, 30, 45 and 90 are. I suppose the other interesting one was when we were down here. So remember we were at pi radians when we got to here, and we've added another 90 degrees or another pi over 2. We're at 1.5 pi. So if I start from 0, this is half pi, this is 1 pi, this is 1.5 pi, and this is 2 pi by the time I do the full rotation. Now, let's use a few of these ideas back in these triangles. You would have seen these triangles before. This is a triangle with right angle in the corner, isosceles, 2 edges equal to 1. Pythagoras would tell me that this is the square root of 1 squared plus 1 squared, or the square root of 2. I have pi over 4 measured in radians, equivalent to 45 degrees. So what if I want to know the sine of pi on 4 radians? Well, sine is opposite over hypotenuse. That's 1 on root 2. What if I wanted to know the cosine of pi on 4 radians? Cosine is adjacent on hypotenuse. That's also 1 on root 2. Isn't that interesting? Sine and cosine of pi on 4 are the same. What about the tan of pi on 4? Tan is opposite over adjacent. So opposite is 1, adjacent is 1, 1 over 1 is 1. The tan of pi on 4. Now you might have learnt these in grade 10 as sine of 45 degrees. etc. But now we'll be talking radians. Now let's look at this diagram. This is an equilateral triangle. It started life, the big triangle is equilateral. So you would probably say 30 degrees in each, 60 degrees in each corner. But remember from what we saw there, 60 degrees is the same as pi over 3. That's why I've labelled this one pi over 3. I've dropped a perpendicular bisector from this vertex down to the middle. Now if the edge of the triangle is 2 and this is a bisector, just to that point there, so I'm only considering the left half, would be a length of 1. Given that that's pi over 3, or 60 degrees, that's 90, it'd be 30 degrees up in this corner here. And as we saw a moment ago, 30 degrees is the same as pi over 6. So we're going to start to think of this as pi over an angle of pi over 6 radians. Now what about this height of the triangle here, h? Well, Pythagoras would say this: 1 squared plus h squared equals 2 squared. So h squared is 4 take 1, that's 3. H is the square root of 3. That's interesting. Now I could use this to give me sine, cosine and tan of both pi over 3 and pi over 6. Let's do this. The sine of pi over 3 opposite is root 3. Hypotenuse is 2. That's root 3 over 2. The cosine of pi over 3, that's the adjacent over the hypotenuse, that's 1 over 2. And the tan of pi on 3. Tan is opposite on opposite on adjacent, root 3 over 1, that's just root 3. So much for the pi over 3 angle. Now what about the pi over 6 angle? Sine of pi over 6, sine of this angle, that's opposite over hypotenuse, 1 over 2. Cosine of pi over 6. Cosine is the adjacent, root 3 over the hypotenuse, 2. And the tan of pi over 6. Tan is opposite, 1 over adjacent, root 3. 1 over root 3. There you are. Now there's a couple of interesting relationships here. The root 3 over 2, root 3 over 2. It looks like the sine of that angle equals the cosine of its complementary angle. Remember, angle and its complement are the ones that add to 90 degrees. What about this one? The cosine of that angle equals the sine of its complement. So it's really the same idea as what I just said a moment ago. And then finally, the tan of an angle, what happens there? It's not equal, it's the reciprocal. So the tan of an angle equals 1 over the tan of its complement. Right, they're handy little things to know. So we have covered radian measure. We have also looked at 2, we call these our special triangles, and the special triangles allow us to quickly write down exact values for sine, cosine and tan of the angles. What are our angles that we're dealing with here? Pi over 3, pi over 6 and pi over 4. Those are the special triangles, those are the 3 trig ratios, and that's a quick introduction, maybe not so quick, to radian measure. Thanks for watching.